Okay, so today is supposed to be one of the payoffs for all of this painful linear algebra we've been doing. So right, because we've done things like page rank and existence of a stationary distribution, cover times, and then we did this. We showed how to do log n space by just doing a random walk. Right, that was a good starting point. To that, we had to do some kind of Uh, I think it's 2mn, but I don't care. Okay. Uh, it's probably 2mn. Uh, then we did here we started doing the spectral analysis where we started looking at eigenvalues to get kind of more refined bounds. Okay, so the first one said, you'll get there in mn steps eventually. Now this is talking about convergence to a stationary distribution. That's for undirected maps. Last time we proved this thing called Cheeger's inequality, which connected conductance, which is sort of something that you can sort of visualize in a graph. They're like bottlenecks in the graph, right? A low conductance cut is like a bottleneck, and we were able to relate that to the mixing time because Cheeger's inequality related this conductance to the second eigenvalue, the second smallest eigenvalue of the normalized Laplacian or something, which corresponded to the spectral gap of a lazy random walk. All right, so much for that. So today we are going to try to take our randomized log n space algorithm and do it deterministically, right? Which is like an insane claim. It's absolutely crazy, and I think the proof will be also absolutely crazy. You'll walk, yeah. So much better is something deterministic versus randomized. Not at all. Yeah, I'm never worried about using quicksort instead of merge sort or this. Yeah. Okay. Also, I think in practice, you're never worried about amortized analysis either. Never really see it. Okay. All right. Oh, well, actually, who am I to comment on practice? I don't know. Okay. So, right. So connectivity. Remember we did this map that 5 of you solved. Most of you didn't. But anyway, you just want to know if S and T are connected, right? And the basic setup is that, well, breadth first search and depth first search take linear time and space, right? It has this feature where we mark the vertices when we visit to make sure we don't visit it twice. And at some level, the question is like, well, is that, an essential feature for a polynomial time algorithm? And so the question becomes, can you start doing it in less space, polylogarithmic space, log space, even log space deterministically? Okay. And really the last two were focused on undirected graphs, and a major open question is directed graphs. So we don't know that we can or cannot. I think the log square n is Savage's theorem. I think it's directed. Okay. So, okay, good. All right, so let me just briefly. Okay, so yeah, so at some level, this is where we left off in that connectivity algorithm. We showed that the cover time was at most mn minus 1. So if you ran for mn steps, you'll probably get there if it's reachable. If not, try again. Or you could actually keep going for mn log n total steps. So the question we're asking today is, what can you do without randomization? Okay. I don't know, should I give you guys a chance to try to think of any ideas? Always go, yeah. Yeah, I don't know if that's well defined in a graph, but anyway, you might get stuck in a cycle, I guess. Um, okay. Any other fun suggestions? Okay. Hashing? Okay. How might you use hashing? Like you try how to make like a pseudo random generator that like sufficiently large enough basically random. Can you deran okay, can you just make a deterministic random generator for the randomized algorithm? You might be able to interpret what we end up doing as something like this. It's going to be quite involved. Um, okay, so recall that every random walk has a stationary distribution. If it's strongly connected, it's unique. It's that eigenvalue. In fact, the stationary distribution for undirected graphs is always proportional to the degrees. Okay, you just kind of plug and check because otherwise it's unique. And we know that we converge the stationary distribution at this rate, if gamma is a spectral gap, it's going to be like e to the minus gamma k. Okay. And the homework asks you if you can get rid of that last square root term. Okay. Now, let me introduce something called an expander graph. An expander graph is a graph where that spectral gap is a constant. Okay, maybe for sake of conversation, it's like 1/2. Okay, so it's any graph where the spectral gap is at least a constant. Often people are interested in constant degree expanders, but I'll be explicit about that. Okay, so and I guess this is supposed to be an expander graph. I mean, if you Google search expander graph, it's what you get, or one of the things you get. Okay, let's look at our deterministic connectivity question for constant degree expanders. This is a special case. Not all graphs are constant degree expanders. But for a constant degree expander, any ideas? Yeah. The number of edges incident to any vertex. So I'm saying it's at most a constant for some constant, 10, 20. I guess in the picture, 3. Yeah? Yes, every vertex has degree at most constant. Yeah? So you approach a stationary distribution very fast. That's what you know, essentially. How can we use it? Okay, well, let me ask a different question then. What is the diameter of a constant degree expander? So of course at most n or something, but can we get a better bound? You can assume it's connected. N over delta, so where delta is the degree, so that'll still be roughly n. Anyone do better than n? Log n? Okay, why? Because of Galton Watson? Okay, so imagine doing a random walk on a constant degree expander. Just start at some vertex, right? So I'll let x be, all the mass on some starting vertex s, okay? And it's going to converge to some stationary distribution that's in proportion to the degree. So if it's a constant degree expander, it's just going to be actually all ones. Still, what do we know about expanders? What's the spectral gap? I guess it's 1/2 here. So what do you get on the right-hand side? Yeah, 1/2 to the k, right? Like I think that square root term disappears because everything's a constant, but it doesn't matter too much. 1/2 to the k. Okay, so it's going down really fast. What happens for like k equals log n? Then okay, if I look at say infinity norms, that's like what's the single worst coordinate? That's going to be bounded above by the L2 norm, which we know how to analyze, right? And if k is like 10 log n, then what do I get for the right-hand side? Yeah, 1 over poly n. Okay. Good. So this thing is basically arbitrarily small. So what does that say about like an individual coordinate of r to the kx, which is your distribution after k steps? It's non-zero. Oops. Right? So this thing is going to be at least, d over 2m minus 1 over poly n, and that's squared in 0. Okay. What does that tell us? So it can, yeah, so, okay. So that means, if you can get there in 10 log n steps, then I guess it means that, well, you can't get there in 10 log n steps, right? There's some path of log n edges from S to any other vertex. Okay. So an expander, we didn't really use the constant degree part. An expander always has small diameter. Okay? You can also try to think of that in terms of conductance. You start at S, and you kind of know you have to have a lot of edges leaving if it's an expander because it expands, right? And then you have a slightly bigger ball, and it has to have a lot of edges leaving, a lot of edges leaving, a lot of edges leaving, but that ball will grow fast. Yeah, so if I'm here and I randomly walk for 5 minutes, and there's a non-zero chance of me ending up at a coffee shop, then I know there must be at least one coffee shop within 5 minutes walking. There's a non-zero chance. Yeah.
So could you repeat, like, what exactly does a constant spectrograph mean in terms of what like the graph looks like?
Yeah, I mean, I guess this is supposed to be an example, but it's just some graph that's always expanding. A complete graph would also be an expander, right? It's well connected. One spot will immediately get you to this uniform distribution, right? So a complete graph would also be very expanding. A constant degree expander is kind of interesting if it exists. And for homework, you're going to do a randomized construction of one. Because on one hand, expansion is kind of saying that things are super well connected. Conductance is high, the spectral graph is huge, a random walk and log n steps, you could be anywhere. Complete graph, one step, you could be anywhere. But this is log n, so it's still pretty fast. Okay. And a constant degree expander is also one that's a very sparse graph. Right? So the number of edges is not that much, and yet somehow it's very well connected. Because log n steps feels like you're walking through a complete graph. Okay? Even though you're walking through a very sparse graph. In fact, the construction you're going to do on the homework is very simple. You sample 3 matchings uniformly at random, and then just throw them on top of each other, and that's an expander with some probability. This upcoming or whatever. Yeah. The last one. Okay. So that would be one example of a construction. Yeah, but they're kind of very counterintuitive objects because on one hand they're very small, on the other hand they're very well connected. Okay, so mathematicians do study this and try to come up with better and better constructions of expanders, where on one hand you want very small degree, on the other hand you want very large expansion, right? So the kind of extreme is something called a Ramanujan graph. Okay, good. All right, so now let's go back to, so we know the diameter of a constant degree expander is log n. Does that give you any hints for a deterministic connectivity algorithm for constant degree expanders? Uh-huh. So in particular, how many random bits do I need to execute one step of a walk in a constant degree expander? So it's a constant, right? What? No, it's a constant degree expander. So if I just want to do one step, I'm at a vertex, and I'm choosing between 10 neighbors, I only need log 10 bits. Yeah. So each random step you can do in just log, constant number of random bits. That means if I'm doing a log n step walk, how many random bits do I need to generate? Again, log n random bits. Okay, so now how do I get an algorithm? Yeah, we just try all the bit strings, right, of 10 log n bits or something. Each one generates a different path in the expander, and one of those paths, if you can get there, it'll go there. Okay, so an expander graph, you can actually solve this deterministic connectivity algorithm because it expands so much. You can always get anywhere in log n hops, and each hop you only need 2 coin tosses or something. Okay, so you only need log n coin tosses to get somewhere with some probability, and then you can just enumerate them. That'll take polynomial time. Yeah.
Why do you think needs to do the random walking? I think it's like a random possible ways to like pick the loose step. Technical plugin.
I mean, I think enumerating the random walk is enumerating all the walks of log n. Yeah, I mean, I think I'm just in the mode of random walks because that helped us get the diameter to be log n. And you can think of it as de-randomizing the random walk algorithm. Yeah. But anyway, it's not too important. Yeah.
These things where
Well, it's undirected. We're assuming the graph is connected. Yeah, so if you can't get there in log n hops, then it's not connected at all. Yeah.
oh yeah.
Right, is a constant degree expander? It's not guaranteed to be connected. Right? Like, we just know that every vertex has less than.
Okay, let's say the component of S is a constant degree expander. Yeah. But anyway, you get the point. Okay. All right, so the point is a constant degree expander, you can actually solve this problem by just enumerating all paths. All right, so good. All right, so that's sort of what we have. We have sort of as a baby step that you do have a deterministic algorithm in constant degree expanders. There's an object you had never heard of before. Now we're going to try to move from there to the general case. Okay, there's kind of a big result 20 years ago to show that you can actually do deterministic connectivity, and we're going to do something kind of very similar in spirit to the expander strategy. Okay, all right, so this is a famous result. So what's the high level idea? So keeping in mind that sort of expanders are kind of easy, are kind of things that we can solve. Our goal is to actually try to take G and turn it into an expander. All right, so what does that mean? Okay, so we're going to try to convert G, our input graph, which of course could be crazy, into a constant degree expander by a bunch of graph transformations. Okay, now these have to be done implicitly because you only have log n space, so you can't just rebuild the whole graph. But we'll kind of like kind of build it in our imagination, and all we have to do is when we actually do things, be able to say, well, what's the 10th neighbor of this vertex? As long as we can kind of simulate these, then you don't have to build the graph out literally. Okay, and then once you've converted G into a constant degree expander, then you can do what we did, where we just kind of de-randomize this random walk approach. We just enumerate the paths in this implicit graph. Okay, so somehow we're going to like overlay some kind of connections or something onto G, so we can treat it as if it were an expander, and then we're done. Okay. All right, so it's sort of crazy. Any questions?
What is the formal definition of a constant degrees?
It's well, constant degree is okay, right? An expander just means the spectral gap is at least a constant. Yeah. I mean, some people might write like a gamma expander is some graph where the expansion or the spectral gap is at least gamma. But for us, it would just be a constant. All right. Okay. Does anyone want to guess how we can try to convert? We're going to alternate between two things, but one of them is more guessable than the other. Any ideas for trying to convert G into an expander? You want to make random walks mix faster. Sorry?
Add an edge.
Add an edge. Well, you want to make sure you maintain connectivity, right? If you add an edge, willy-nilly between two things that weren't connected, you're going to get a different answer. Yeah.
Just like travel randomly for some bit and then just connect both.
Maybe I can travel around and then add connections back or something. Yeah. I think that gets to sort of the first idea, which is just kind of graph powering. I can replace G with the graph induced by, I don't know, all 5 edge walks. Right? So I add an edge between A and B if I can get from A to B in 5 edges or something, right? So now one step simulates 5 steps or something. So graph powering. The second one is crazy. At the moment, it's just a name. It's going to be called the zigzag product, but I'll explain when we cross that bridge. Okay. All right. So, as a preliminary, we can assume that G is a regular graph with constant degree. How?
Because if it's small, you can transfer.
Yeah, if it's a very high degree thing, I can just like transform it and into something like a 3-degree thing by kind of splitting each vertex with a cycle. Okay? Something like this. So we're just going to assume G is constant degree to start. Okay. All right. So Graph powering, right? You take a graph and I don't know, g squared would add all pairs of edges into edges. G cubed would add all triplets, right? So you get the idea.
The original edges between the Jason rings.
Yeah. So g squared looks funny, because the evens can't reach the odds when you're only looking at the. You have to take exactly 2 steps in g squared.
Oops.
Those are self loops because you go there and back. So if well, okay, if I let the random walk matrix for say the kth power graph is the exact same as taking a random walk for k steps on the original graph. So r to the k will coincidentally be the random walk matrix for g to the k. And what are its eigenvalues relative to g or r's? They're just raised to the kth power. Okay. So in particular, what happens to the spectral gap? It's going to get bigger. Oh, well, okay. Yeah. It's going to get bigger, something like this. 1 minus spectral gap to the k because of this 1 minus nonsense. But if gamma is pretty small, and I think we're just going to do like k is 2, and we're worried about gamma being small. Once gamma is big enough, you have an expander, you're done. So this is basically 1 minus k times gamma. Okay, so the spectral gap is just widening by a factor of k. Or no, sorry, it's just k times gamma. 1 minus gamma. Okay. All right, so that's good. The spectral gap will just increase. As long as gamma is very small, if you do g squared, you're basically doubling the spectral gap. You give back a little on a second order term, but that's not a big deal. Okay, but what happens to the degree of the graph? It does increase, that's said. Okay, but what does it increase to? Yeah, squared, or if you do g2, it's going to go squared. If you do g5, it's going to go d to the 5, right? Because now you have an edge for every 5 edge hop, and it's d times d times d times d times d. Okay. All right, so it's going to go up to d to the k in general. Okay, huh? Well, because we want the degree to be small. What we're looking for is a constant degree expander. So like we can get more expanding, but now we're trading off the degree. So I can't just exponentiate this and be done, right? We're assuming uniform the same degree. You can think of it as maximum degree. I think it will be matter. Okay. Any other questions? Yeah, I guess if you're worried about the small degree vertices and stuff, you can always add self loops as well and make the degree uniform to start. Okay, good. All right. Now here comes the wilder and crazy one. So we know how to actually increase the expansion pretty well. Okay, if you just take the power, the spectral gap's going to go up. Because I don't know, now 1 hop is simulating 2 hops. Of course, you're going to mix faster, twice the rate. If you do it again, then it becomes 4. If you do it again, it becomes 8 times, right? So you're getting this nice speed up. The only issue is that when we do this, the degree gets bigger and bigger. So we need something to bring down the degree of the graph, okay? And we want to do something that's sort of like, doesn't lose too much of the randomness. Okay, maintains, so you're going to give up a little in the spectral gap, but we're hoping not to give up too much. Okay, so one way to think about this is the following. So, you have some graph, you take into a power, at some level you're happy with the progress you're making on the expansion and spectral gap. Okay, but you can't really do the random walk you want to because the degree is too high. Every choice is going to use too many bits. Okay, so at some level the question is, can I sort of simulate a random walk in a relatively high degree graph, still constant, but like, it's getting up there, with fewer bits? Okay, any ideas? Yeah, no, we're not going to do hashing. Well, okay. What if you had access to some constant size, constant degree expander? Right, so a mathematician went off, made you a nice expander. He'll give you an expander of any degree you want and any size you want. Okay. So in particular, suppose I gave you a constant degree expander with exactly d vertices. Okay, so you can try to do a random walk on that one, but what does that mean?
Next you end up is the path that you choose from that original graph.
Okay, so I kind of think of this as like, you're here and you want to roll a dice, but you can't roll like a normal dice. Okay, so here I kind of think of this as some kind of like fake dice. So over here think of this as like some pseudo random number generator inside your computer. Okay, so your computer state is somewhere here. Okay, and this is a constant degree graph. And you don't have that many random bits to spare. So you don't have enough random bits to choose one out of D, but you have enough random bits to take, say, one step in here. Okay, so you'll take one step and it'll go here or something. Okay, now what I want to do is I want to take the name of this vertex and interpret it as a choice here. Okay, so what we'll do, what we're going to do is going to get D to get matched up. So this will have D vertices. So 1, 2, and we're going to name all the vertices. Maybe this is D or something. So the number of vertices in our expander is going to match up exactly to the kind of degree of our graph. Okay, so when I take one hop here and this says, okay, you went to vertex 17 in your expander, I'm going to go all the way around and say, okay, I'm going to go to neighbor 17. Okay, and I go to neighbor 17 and I'm going to find myself in the same situation, a relatively high degree vertex. Okay, and I'm going to take another step in the expander. So again, there's only degree 3 in that expander, so I only need 2 bits. And that's going to move to another vertex in this expander. And that'll be, I don't know, number 23 or something, right? And so I'm going to go and I'm going to say, oh, okay, this is neighbor 23 of this vertex. Okay. So I'm going to use this as some kind of like pseudo-random, not perfect dice. Okay. Yeah.
You start with it, right?
It won't matter where we start. So what's the intuition? So of course, this is not, what you really want to do is choose a completely random vertex every time. And this is not that, right? When you're at a vertex, you only have 3 choices or something, or 5 choices. It's not that. But expanders in the aggregate, right, in some kind of quantifiable way, when we do the analysis, looks more and more like a complete graph. So you're hoping that as you take some random walk in here, which maps to various choices in the original graph, it's not truly random, it's not fully random, but it feels random. It's kind of random. I mean, we can analyze it and show it's very nearly random. What we're going to try to show is that, the difference between this pseudo-random walk and a truly random walk has something to do with the spectral gap of H, right? If the spectral gap of H was like fully maxed out at 1, then it would be a completely random walk. And then it would be completely random over there. Spectral gap is, I don't know, 1/2, 3/4, something over here. So you won't quite be perfectly random, but it's going to be pretty random because a random walk here does in the aggregate look like a stationary distribution. It is true that from one to the next, it doesn't quite, but in the aggregate, it does. And when you do the math, things get aggregated. Yeah.
More space.
So this is a constant degree expander of constant size. The mapping? Well, so I'm just counting from 1 to 100, so I need at most log 100 bits for each one. So it's still constant. So what's going to happen is we're going to have our start with like a very, constant degree graph, and then we're going to square the degree. It's going to go up moderately, but it'll still be a constant, and then we'll bring it back down. And we'll go up moderately, bring it back down moderately, but it'll still always be a constant. So you can afford to write all these things down. And I think we'll have to reuse the same graph for when we do this over and over again too, in case you were concerned. Okay, good. Okay, so that's the high level idea, right? Of trying to sort of fake randomness, right? I think this is I guess hashing also simulates this, right? Kind of some sort of fake randomness, but this is a little different. Okay, so the zigzag product is going to try to do this. So let's first try to figure out like what's the natural thing to do. Okay, so as you do this kind of thing, you have your position in the graph, and then you have your kind of state in the pseudo-random generator, right? So I can take my graph in that small expander, and I'll look at kind of something like the product graph, right? Because each step, I'm going to make a move in G and I'm going to make a move in H, right? But it won't be exactly like that. So, okay. All right. So, in other words, so I don't want degree D. I want the degree to be much smaller, right? So what I want is everything to have degree D0, where D0 is that smaller constant degree of the expander. All right, so what would I do? So right now I'm at a vertex in G and a vertex in H, and I want to get the third neighbor or something. How would I do this written out? I'm in G, I'm in H. Yeah, so what does a step, I'm wondering you guys try to guess, what should a step look like to kind of simulate this thing we've been talking about?
Make H one of its neighbors.
Okay, so we'll take a step in H, right?
Maybe it's next year.
And then we'll look at okay, yeah, perfect. So first, I'll make a step in H, okay? And then I'll just look up the index of that vertex, and I'll move the G vertex accordingly. Okay. All right, so what is the degree of this kind of auxiliary graph? D0. So everyone has only D0 choices corresponding to choices in H. Okay, so that actually accomplishes quite a lot. But what's the kind of, there's one kind of basic issue.
It's not connected.
I think it is actually connected, but well, we'll eventually show it's connected. But there's another issue, or maybe did this issue here, but simpler, easier to see.
You can't go through it.
Sorry,
But you have limited choices now.
yeah, what?
Limited choices.
Well, that's true, but that's something that's actually going to be a feature. But there's kind of one, yeah.
Vertices.
The vertices do go up a little bit, but that's actually going to be tolerable. These are actually all not wrong answers, but there's one kind of glaring.
It's clever.
Degrees.
It's not an undirected graph, so this is not actually a symmetric thing we made. Okay, so all we have to do is take the same idea and make it symmetric, and then it's going to look a little more complicated. But all we're doing is taking this idea and making it symmetric. Okay, so what we're going to do is now, instead of doing kind of one choice in H, you're going to end up doing two choices in H. The first two steps will be the same. I'm going to move in H, use that to move in G. And now you're going to do this like reverse lookup. It's a little bit odd. Okay. So you've already moved in H and used one of your sets of random bits. Okay. And you use that to move in G. And then so G, you move from V1 to V2. And you move from V1 to V1's 10th neighbor or something. But then you look at V2 and say, oh, V1 was the fifth neighbor of V2 if I went backwards. Okay, so you assume everyone has like their neighbors numbered. Okay, so you went from V1 to V2, but just because there may be a different index in the opposite direction. What is the index of V1 relative to V2? And so that will be I3. So you're going to teleport an H to I3. Okay, so you're going to use the H to first move in G, and then you're going to use your movement in G looking backwards to move in H and teleport in H. Okay, and then you're going to take one more step in H.
How does that solve the problem?
Well, apparently, if you look at this carefully, you'll find that it's reversible. Okay, so morally, we're still just trying to do this. Use H to simulate a step in G, and then we have to do some hacky stuff to get it to work. Okay, so you should be able to find indexes that always go in the opposite direction. Okay. Right. Okay. So ultimately, what's the degree of this? It's going to be d0 squared because we made two movements in H. So we stepped in H once to help choose G, and then G sent us to some crazy place in H, and then we took one more step. So this last step. So you end up doing d0 squared choices. All right, good. So the degree is going to be d0 squared. I think if you contemplate it, you'll find that it's undirected. Okay. Does anyone have like a one sentence way to see this? Because I don't. Well, okay. Anyway, we'll just keep going. Okay, so this zigzag product, let's tally everything up. Okay, spectral gap. Okay, that's going to be impossible to guess, but the other two you can guess. Okay, so how many vertices, if G had, G had n vertices, H had d vertices? N plus d? Any other guesses? N times d is looking a little bit more like the product graph, though it's not exactly. Okay, what's the degree? We just did this. D0 squared. So we're back to some controlled constant. And of course, this is unguessable. So we're going to show that the spectral gap is gamma g gamma h squared. Okay. Now the spectral gap's always between 0 and 1. So the spectral gap does go down. We want the spectral gap to get bigger and bigger and bigger, but it does go down, right? But insofar as h is an expander, you're hoping that gamma h is closer and closer to 1, so it doesn't go down by too much. Okay, so you're able to reset the degree. You add a few more vertices. And you lose a little bit on the spectral gap. Okay, but you fix the degrees. Okay, so good. So let's tally everything up. So, for example, okay, in general, GK will have how many vertices if it started with n? Just n. The number of vertices has not changed. But what was the degree? Excellent. And then what would the spectral gap be? Yeah, something like this. Okay. And then we just did the zigzag product. It's going to look like this. Okay. So now what happens when I square it and then apply the zigzag product with an expander where all the degrees work out nicely? All right, so how many total vertices? You- okay, well, this is your strong suit. What about the degree? All right, d0 squared. And then what does spectral gap look like? Same thing, you have two choices. Okay, it's going to be kind of like multiplied together, something like this. Okay, so the vertices go up a little bit by constant. The degree gets reset to something nice. So basically, the degree is going to jump from d0 squared to d0 to the fourth to d0 squared to d0 to the fourth, back and forth. And then you have this kind of spectral gap, and the question is, does this actually make improvement? So that's the spectral gap for H. Yeah, so it's going to be like a constant because H is this magical expander. Okay, so I have some example worked out. So if gamma G is, say, at most 1/16, and gamma H is like at least 3/4. Okay, if 3/4, we could have made gamma H 1/2 and it made gamma G smaller or something and gotten the same effect. We just expand this out first. Hopefully that's correct. Okay, you get something like 2 gamma G gamma H squared. This is the gamma G squared, right? Okay. Now the key thing here, right? So gamma G is small. That's the bad, we're not done if gamma G is small. So this 2 gamma G is going to dominate the gamma G squared. Okay, so this is basically 2 gamma G gamma H squared. So you basically double, but then you give up 3/4 squared. And 3/4 squared should be a little more than 1/2, 9/16. So you double, you give up a little less than 1/2. So overall, you make progress. Yeah, I think I was lazy. I didn't really calculate exactly. but the spectral gap will go up by some constant, okay, for these particular values. Okay. So you have actually made progress. Yeah.
Increasing the spectral gravity, make it constant.
Great. So how okay, so gamma G is at most like 1 over poly n to start. Okay, that's not too hard to show. How many times do I have to do this to get it up to a constant? How many times do I have to multiply by 1%? No. So you got 1 over poly n to start. No. Log n times. Yeah, you'll need to do it like 100 times to get to double. So you start at 1 over poly n, every 100 times you double, if it's 1.01, right? So after, log n times, it's up to at least 1/16, and you're done. Yeah, it'll grow even faster at the very beginning when gamma G is very, very small. But okay, so you only have to do this log n times. So how do you actually take advantage of that, though, in the algorithm? Right? You can't, because we can't just construct this algorithm explicitly. Okay. So for space usage, all we need to do is to be able to answer questions, in limited space, I guess log n space. Given a vertex V, what is its 10th neighbor? What is its 11th neighbor? Where for whatever crazy auxiliary graph you're at some point in the stack. Okay. And so you just go through it carefully and implicitly. I'm not sure if what I wrote is careful enough, but let's say you're in G squared, right? And so, the degree is like D squared. You could think of that as two choices out of D, right? So I'll say the I1, I2th neighbor. Okay. And well, okay, first you need to figure out the I1th neighbor. How do you do that? Well, in particular in G. So you're trying to figure out neighbors in G squared, right? But we can just do it one hop at a time. So first you figure out the neighbor in G, but G itself is some crazy graph, right? So you can recurse, and you go down the recursive stack. You put kind of constant amount of space on the stack, and you keep going down, and you bubble back up. And then you get some vertex, and then you figure out the next neighbor. You go down, you go up. See, the nice thing about space usage compared to time is you're only worried about the max space, so it doesn't like sum up. Okay, so you can do this kind of recursion trick, where you just, how deep is this stack is really all you're concerned with. Okay, and then I think you just return V2. Okay, so you can do this. Maybe with a little bit of care. And the zigzag is something similar, right? Okay, zigzag is some crazy thing, but all I need to do is be able to simulate a step. All I gotta do is be able to simulate a step. So if I want to figure out the K1, K2th neighbor of some particular vertex in the graph, right? We just do say, okay, I first figure out how to move in H. That's easy. That's everything's a constant. I don't have to recurse for that. But then I use I2, to figure out a certain neighbor of V. Okay. Now the third one's a little bit trickier, right? Because you need to figure out the index I3, where V1 is the I3th neighbor of V2, that reverse lookup thing. Okay, how can I do that? We can just loop. So we just enumerate and you recurse on each guess. What is the 10th neighbor? Is it this? Okay, great. Okay. And then you do one more step in H. So you can simulate and work with this graph without constructing it explicitly. Okay. Maybe I should go a little slower about, yeah.
A little bit more about this like version. Are you like doing like
Yeah, so you should only need like 2 bits to say I2 or I1 or something, right? So we just need to you just need enough memory so that when the recursive call comes back, you can put it back together. So you just kind of shove some constant memory on the stack, and then the stack will fill up as you do recursive calls and then come back. Something like this. I think to write out explicitly, you might want to be a little bit more careful, but yeah.
and the I guess like we were just like concerned about the space we're at, not really.
Yeah, this is not like a great fast algorithm. Like nobody needs maybe there's some like robot on Mars that needs a small space algorithm or something, but in general, or maybe like your Roomba, which is basically doing a random walk or something, right? Like so, okay. But in general, okay, it'll still be polynomial time because it'll be log space. And so you gonna enumerate stuff will just be polynomial time, but yeah, it's not super fast. I think it's just more like it's an achievement of human imagination. Okay. All right. So well the real meat is trying to analyze this random walk. This is where we'll all start groaning, but like if you hated tensor products before today, just wait till what we have coming up. Okay, so we're gonna write the random walk. Okay, oh, that's right. So all we really need to analyze is the spectral gap for the zigzag product. Everything else, like the spectral gap with the product graph, the degrees, the vertices, things like this, that was a non-issue. All we really got to do is figure out the spectral gap of the zigzag product, and then we're done. So there's only one thing left. Okay, but of course we haven't done any math yet, so we have to make up for it. Okay, so okay, let me explain. I'm gonna write it something like this. So okay, the first term is supposed to simulate, the first and last term is supposed to be the random step in R and random step in H. I will explain formally what the tensor really means, but I is sort of like stay put in G. You apply the identity matrix to G. And RH is saying take a step in H. Okay. So that's what it's ultimately going to read out to be. It's going to coincide with something called a tensor product of matrices. But it's otherwise going to be exactly kind of what you want it to be. Okay. And in the second one, that middle step is actually deterministic, right? Once you've made your choice in H1, you just follow 2 steps deterministically. Okay. So I'm just going to call this Z. Okay. I should point out Z is still a random walk matrix. It's not very random. You just go from one place to the next. It's a degree 1 random walk matrix, but it's still a degree 1 matrix, which is helpful. I mean, random walk matrix, which is, say, at least know the eigenvalues are between -1 and 1 and things like this. Okay. All right, so good. So that's we're going to try to analyze, the spectrum of this thing, and we're going to kind of decompose things according to this. Okay. So what's the idea? So the idea is that RH is supposed to almost look like a uniformly random distribution. Okay. So let's say that I let S be kind of like the all ones matrix divided by D or something, right? This would actually be the random walk matrix of like a completely connected graph plus a self loop at every vertex, so that every step you can go anywhere next, right? Just all 1 over D kind of uniformly everywhere. Okay, so that's sort of like ideal. It would be very great, ideally RH would behave exactly like S. If I replace RH with S, actually I think we have it down here. Yes, okay, so morally, what we kind of want to show is that, I probably should have wrote RH instead of S, RH instead of H. Okay, it should be something like this. But I keep telling you expanders are kind of like complete graphs. So you're hoping that the random walk behaves like as if it was completely connected. There's going to be some quantitative difference, but qualitatively you're hoping they're more like than unlike. Okay, so okay, okay, that's fine. So imagine I replaced this used to be RH here, right? Before you took a random step in H, you did a zigzag product, and then you took a random step in H. Here, suppose I took a completely random vertex in H, did a zigzag product, right? So, okay, so this would just be sampling a completely random vertex in H, and then Z will use that coordinate you got to go somewhere, right? Yeah. So, in other words, how can I think about this? So I take a completely random vertex in H, then I follow the zigzag product, and I go to that neighbor in G. and then I take a completely random step in H. So what does that kind of look like overall? Or a completely random vertex in H? Yeah. Yeah, so in terms of G, I'm doing a completely random walk. And in terms of H, I'm just sampling another random vertex. Okay. So in other words, oh no. Okay. So well. Okay, so you're really just taking a random walk in G and H at the same time. H kind of mixes immediately. So if you're thinking about how long it takes to mix or the spectral gap, you can go through this more carefully, but you're really just bottlenecked by how long it takes to mix in G. Okay, I'll give you the tools to analyze this formally in a moment, but this, which can be written as this random walk in G while simultaneously going to any vertex in S, will have the exact same spectral gap as G. So that would be great, right? Like if our zigzag product maintained the same spectral gap, you didn't lose anything, then we'd just be done, right? I increase the spectral gap, and I do a zigzag, but I get to use S instead. The spectral gap stays the exact same, and then we'd be very happy. The only problem is that, of course, S is a completely connected graph, so you're not winning on the degrees at all. Okay? All right. So what our approach in our analysis is going to look something like this. So this is this random walk in H, zigzag random walk in H. And what we want to show is that insofar as RH is similar to S, you're hoping that this actual thing we're analyzing is very similar to this relatively simple ideal thing, right? Because this is really just random walk in G. And this will have pretty good spectral gap comparable to RG.
What's that tensor product like?
Well, I'm glad you asked. Okay, so first, so tensor product and graph, it's going to be what we normally call a product graph. Okay, so you have vertices for every pair of vertices, and you have an edge for like every pair of edges. Okay, so in one step, you move in both graphs simultaneously. Okay, so normally what we call a product graph. I'm calling it tensor product graph because we model the random walk matrices is actually going to correspond to what's already known as the tensor product. Yeah.
It's just the same operation as the other product.
No.
Yeah, kind of, but it's going to be kind of more abstractly interpreted, right? Because we're not taking the outer product of vectors, which is probably what you're used to. Okay, so like I've already burdened you with this notation, right? You take two vectors and you get this rank one matrix, which is their outer product. You're probably used to UV transpose or something. All right, so tensor product of matrices. Okay, if you do like, I don't know if anyone's taking quantum class, but there are fields where this operation will come up quite a lot. Okay, so you're taking a tensor of two different matrices. One, I guess, living in m-dimensional space. The other living in n-dimensional space, n to n, m to m. Okay, I think for us the matrices will always be symmetric, but in any case, you can define it in general. So it's going to take us. Basically, it's going to have this effect. So you can think of it as a linear map from the space of linear maps from m to n to the space of linear maps from m to n. And it's going to, I guess, apply something like this, ACB transpose. I think a more helpful definition, okay, is to look at this special case. So at some level, like any matrix C can always be decomposed to a bunch of rank one terms, right? That could be this SVD, but there's a million different ways to do it. SVD will give you a very compact one, but there's a million ways to take your matrix and turn it into a bunch of rank one terms. So if you define it for rank one terms, then by linearity, everything else follows. Now, in this case, if I apply this tensor product of A and B to a rank one term induced by C and D, then you're going to get this rank one term, AC outer product BD. Okay, so you can show that these two definitions are equivalent. In fact, this is the one I remember, and then I have to take out scratch paper and try to figure out what it means in general. Okay, sort of a funky object. Okay. Okay. Now, what are the eigenvalues of A tensor B? Like, what could they be?
The product of that.
Oh, just all of them.
Okay, of A, of B, of both. What are the eigenvectors? What did eigenvectors look like? So for example, let's look at this, right? Suppose C was an eigenvector for A, and D was an eigenvector for B. Okay. Then inside here you would get something like lambda C, 10, or maybe I'll write lambda 1, lambda 2, D, where lambda 1 is whatever the eigenvalue was for C in A, and lambda 2 is whatever the eigenvalue was for D. Okay. So overall, you're going to get like lambda 1, lambda 2, the rank 1 term induced by C and D. Okay. So what does that mean? That means that all the pairs of eigenvectors for A and B, their rank 1 term will give you an eigenvector for this crazy tensor product. So the eigenvalues will all get multiplied. Okay. And then to see that those are all the eigenvalues, it's just a counting argument because you're going from m times n to m times n, so you know there's m times n eigenvalues. Okay. All right. So we're kind of treating linear maths. It's confusing, I know. But anyway, because there's going to be eigenvalues equal to the dimension of this. The number of eigenvalues equals the dimension of space. Counting with multiplicity. Well, okay, but I'll count zeros to fill it out. Okay. All right, but these are going to give you all the eigenvalues. So all the eigenvalues are going to be products. There's not going to be anything else. Okay. All right, that's going to be useful because for us, our random walks often look like, I don't know, this is something simple, this is something separate. We know them separately. Now we know what their kind of combination looks like. So I guess as a special case, yeah, this is a little bit confusing, isn't it? No, I don't think it's important. Okay, so maybe I should mention that if you have two graphs, this probably deserved a slide. So if their random walk matrices were RG and RG1 and RG2, okay, the random walk matrix for the combination is going to be RG1 tensor RG2. Okay, whatever crazy thing that is, right? If you really want, you can take the definitions and work out what all the coordinates will be. That's fine. Yeah. Okay. And you can sort of see that here. So, if you had some distribution P over here and a distribution Q over here, the outer product P Q is sort of like the distribution over the product space where you pick a vertex on the left side based on P and a vertex on the right side based on Q. So it's kind of this rank 1 mixed distribution, right? This is kind of special. But if you apply that into here, you'll get RG1P, RG2Q. And that's really saying, okay, I have some distribution on the left, some distribution on the right. And then I take one step on the left, give me a new distribution on the left. I take one step on the right, give me a new distribution on the right. Okay. All right. By linearity, that will then cover all distributions on the product graph. Okay. I won't dwell on too much. I think more importantly is maybe just seeing how it can be useful.
Maybe it's part of the A tensor product B eigenvalues and are the eigenvectors just like if they like matrices, right?
Yeah, these will kind of look like matrices. Well, I think that vectors in the more general sense of the word is just something living in a vector space, which is things where, if you're summing and it stays in a space, you have a vector space. Yeah, so it's a little awkward because we're lifting all the usual linear algebra, right? What we used to call vectors or matrices and stuff like this, but actually the same logic is applying exactly. And you can actually kind of interpret this tensor product of matrices as doing like a rank 1 term if you thought of those matrices as vectors in their respective spaces. Okay. It's not worth, I mean, it's not worth we could just sit and think for like 10 minutes. But okay, let's just try to use this. I'll tell you what you need to know. Okay, now if I look at the random walk matrix on H, right? Our original expander. It's a constant degree expander, so uniform distribution is just the stationary distribution is just uniform, right? Because proportional to degree, but everyone has the same degree. So you know that the first eigenvector looks like 1's divided by square root d, which is just d is the number of vertices, remember, in our constant degree expander. And so that means that this first term looks like this. 1 times 1 over d, that was that same thing s we had earlier. Okay, so you can think of RH as, if I swap out that first term, okay, so the first term, which is the outer product induced by the stationary distribution, is just S. S is like that matrix that takes everyone to everywhere. And then you have all this noise, right? This is the ideal. RH is ideally S, that's the biggest eigenvector that's kind of dominating the behavior. But then you have these things that make it imperfect, mu2 through mu n. But you're hoping with a large spectral gap, all of these other coefficients are pretty small in absolute value. So you are hoping that the effect of these guys are small, and it's mostly S. If you think of it as like a composition of rank 1 matrices. So in particular, like if I subtract out, the spectral gap of H times S, what happens to the remaining eigenvalues in like RH prime? So remember, mu2 is at most 1 minus gamma. Mu n is at least 1 minus gamma. Yeah, so now all the eigenvalues, if I just rip out a small piece of the first eigenvector, are now in this range, gamma h minus 1. Okay, so the spectral radius, or so to speak, of this, trim off a little bit, is nice and small. Okay, so now let's look at this thing we want to analyze. Okay, it's actually not going to be not that much left actually, but it's going to be a little magical. Okay, so what I'm going to do is I'm just going to plug in first. I'm going to replace RH with sort of this small matrix, small spectral radius matrix, plus this gamma h times kind of perfection S. Okay, and I'm just going to factor this. So it's going to seem like a lot, but all I've done is kind of factored it. So that should be gamma h, but you have this gamma squared where you have S on both sides. And then you have gamma, and then these are really morally the same, but they're slightly different, right? 1S, 1 RH prime, 1 RH prime, 1S. Different orders, so you have to repeat the terms. And then you have this thing where you have this kind of small thing times z times small thing. Okay. And what I kind of want to show is that, the spectral radius is good. So if I what I really want to show, right, is if I take any, eigenvector that's orthogonal to the stationary distribution, right? Because I'm really worried about the second eigenvalue, and I mean all the eigenvalues that are orthogonal to the first eigenvector. And if I, this kind of thing, right? This will capture the spectral radius if X is orthogonal to that first eigenvector. And I want to show that this is kind of small because the spectral gap is big. Okay, so I want to, then we can put absolute values around everything, but some of I want to analyze each of these things and show that they don't kind of expand too much. No, this should be an H. Yeah, and the type is going to show up on the next slide too. This seems like the same slide. Okay, now one tool that's going to help us is something called the operator norm. I know I'm throwing a lot at you, but the good news is we're going to get a deterministic algorithm for connectivity, and that's exciting. Okay, the spectral norm, our operator norm, is it also spectral norm? Anyway, which you've maybe seen in a linear algebra class before, is defined by, this is defined for any matrix. Out of all unit inputs, what's the largest magnitude of the output? So how much can it stretch a vector? Okay, and if you expand out the inner product thingy, you can replace that norm with square root of x ATAX. Okay, now where have we seen this kind of thing before? Especially including this. Sorry? The what? The Riley quotient. This has to do with the first eigenvectors and things like this, trying to maximize this sort of product over this. So this is the square root of the maximum eigenvalue of ATA. So ATA is automatically symmetric no matter what A is. Right? It's actually going to be positive semi-definite as well, so eigenvalues will all be positive. Okay, and if A is symmetric, then ATA is A squared, right? So that's going to get you the maximum absolute value of any eigenvalue of A. Okay. All right. Okay. So at this point, it's just like some symbols for something that already exists. It's not that exciting, but you have these inequalities that are not too hard to prove. You just go through it slowly. You plug it in X, and you basically apply triangle inequality or Cauchy-Schwarz or whatever. Okay. So, for example, the norm of A plus B is at most the norm of A plus the norm of B. So you have this like triangle inequality. And so basically, it is a norm. In a math class, we would like prove everything slowly, but you know, we're all friends. You also have this Cauchy-Schwarz looking thing. Okay, the norm of A times B is at most the norm of A times the norm of B. Also for tensors, right? At least for symmetric ones, right? We know the eigenvalues are made by multiplying the eigenvalues together. So you get the same kind of thing. Okay, the operator norm of the tensor of A and B is at most the ones separate. Okay. All right, we have 5 minutes. We'll do our best. We'll be fine. Okay. The more time, the more you realize there's bugs. So this is kind of perfect. All right. Okay, so I thought there was something here. No. Okay. All right. So let's look at this first term. Actually, this is probably the most sophisticated one. Okay, so if I look at this, right, just to remind us, the S's are each picking a random vertex in H, right? And the Z is some kind of deterministic thing. And we already saw that, you know, at the end of the day, this whole thing combined is doing one random step in H and taking a random vertex in one random step in G and a random vertex in H. So you could have written it as something like this. On the G side, you're taking a random step. On the H side, you're picking a random vertex. Okay. All right. So what do the eigenvectors and eigenvalues look like? In particular, what is like the stationary distribution of something like this? Yeah, it's going to be stationary distribution of G tensor kind of uniform over here. Okay. And, you know, S only has one eigenvalue of value 1, and the rest is all 0 because it's a rank 1 term. So all the eigenvalues of this thing looks like just the eigenvalues of G plus a bunch of zeros, right? Because it's going to be eigenvalue of G times 1, eigenvalue G times 1, eigenvalue, until you get them to 0, eigenvalue G times 0, that's 0. Okay. And so the eigenvectors are all going to look like either, yeah. So as a result, yeah, so that's the stationary distribution. And one thing to point out is that this the same stationary distribution as for G essentially. Okay. And so the spectral gap, because all the eigenvalues are basically the exact same, because S is not doing anything, just multiplying by 1 for you, and it's only giving you one of those. The spectral gap is the same. Okay, and the first eigenvector is the same. In fact, all the eigenvectors are basically the same. Okay, now, okay, so much for that. Now let's look at the second term, which is very similar to the third term because that's just swapping order. We'll directly analyze the second, and the same thing will work for the third. Okay. Now for the second one, we're going to try to use our operator norm tricks. Okay. So I'm going to look at the operator norm of this messy looking thing. Okay. What can I do to try to make some progress? Sorry? Yeah, which inequality? Okay, so we'll start there. Okay. All right, so I can split this up. This is where operator norm gets kind of slick. Okay. All right, so what did eigenvalues of I tensor S look like? Sorry? Yeah, it's going to be at most 1. Okay, no big deal. All right, what about Z? Z is this crazy zigzag thingy. You take a step based on H, and then you look backwards, and then you move around in H. Why? Yeah, okay, that's fancy, but it's still a random walk ultimately. It is indeed a It is indeed a permutation matrix. I mean, in a sense that it's just degree 1, but I just think of it's a random walk, so it's at most 1. Okay, now how about this? Sorry. How about this third term? So you have 1 and 1. So remember this trimmed off, that gamma piece of the first eigenvector. So everything left is inside that 1 minus gamma in absolute value. Okay, so you get something like this. You multiply that together, you get 1 minus gamma h. Okay, the same analysis will work for that third term. Yeah, so we're gradually kind of stacking up some bounds on the right-hand column there. All right, now let's look at this one. Again, we're going to analyze the operator norm, the spectral norm. What should I do first? Split them. Okay. What's the first one? What's the second one? What's the third one? Go all together. It's something like this. Okay, so you break them apart, and then somehow, I agree, the tensor is kind of a new thing, the operator is kind of a new thing. I didn't prove all those properties, but they're not hard to prove. You just go through it, check with X and stuff. They're left as exercises in the notes. Okay, they're somewhat straightforward, although maybe the notation is sort of new to get used to. Okay, but then we're chopping up, what is sort of a crazy and wild random walk, right? Suddenly things seem very tractable. Okay, so let's put everything together. So again, the stationary distribution is just a uniform distribution. So the first eigenvector is the all ones matrix or something scaled. So let's look at any vector x that's orthogonal to that, right? And we can of course break this down as something like this. Well, this is just a memory game. Anyone remember what the first term was? This was the gamma h squared. So the gamma h squared is coming from here. And this is because this thing is really just the random walk on G times S, right? So you still get the same spectral gap. So X, remember, X is orthogonal to the first eigenvector. That's why the 1 minus gamma G comes out. That's the one subtle point. And the next one just come from the inequalities we had before. So that's gamma H times 1 minus gamma H times 1 minus gamma H, 1 minus gamma H squared. We just did those calculations. All right, what happens when I add all these up? It is true. If you sum things up, you will get a sum. Okay, what sum will you get? All right, did you guys get this? Are there smart kids? Okay, this is what it should be. Okay, so it all sums up like this. So that gives us a bound on the magnitude of the second eigenvalue, right? Which means that the spectral gap is 1 minus this. That's how you get gamma h squared gamma g. Okay, so but I think what you see kind of going on here is originally this RH, we did kind of break it up into one part S and one part RH prime. RH prime was small, and that S part gave us the real mixing we're looking for, right? It's that first term that gave us gamma h squared 1 minus gamma g. That's really doing the work for us. That's where the gamma g comes in. Okay, so that's the whole proof, right? We show that the spectral gap is gamma g gamma h squared. If you look back on the analysis, you'll see that we kept trying to compare RH to S, and that difference is kind of directly reflected in the analysis. And that's the whole thing. So once you can show that this zigzag combined with the product graph is actually a win, you reset the degree, but the spectral gap goes up by constant. You just do this log n times. I mean, just is doing a lot of work there, but yeah, you get the idea. Okay, so that's this thing. So you can do log n deterministic. You know, ultimately you just enumerate paths in this crazy implicit graph. Okay, thank you.